Hello. Sorry about the delay. All right, now we're back to more probabilities, like real probabilities. So this section is titled, kind of a confusing title, or, and problems. How often do you see the word and right next to itself twice, and it actually makes sense? So that's an interesting title, but I guess this section will cover, like if you said, what's the probability of me, if I'm dealt two cards from a deck of playing cards, um, getting a king or a queen? You know, how do you deal with that? Is there a formula for it? That kind of thing. Or if I'm dealt two cards, what's the probability that both are kings and both are red cards, or so, you know, something like that. So or and, of course, or is different than and, because or you're kind of, you imagine the probability is going to be higher because you're not as particular. If I say I'll take this or this, then I'm kind of more open to things. Whereas and, I need this to happen and I need that to happen. I need both. So it's going to be two different kind of formulas. But what do we have first? So or probabilities. What, Nana? Hi, Nana. Okay. Oh, dang it. Sorry. Okay. So if you want to calculate the probability of event A happening or event B happening, think A and B are events. Like we said, A is getting a king, and when you get a couple cards in a standard deck, and then B's maybe getting a red card. Something like that. So two different events. What's the probability of one happening or the other? Okay, so as you can see from the formula, it's the probability of each added together, subtract the probability of the two happening at the same time, A and B. So and there'll be times where that's easy to calculate, and there'll be times where it's hard to calculate. So we'll talk more about probability of A and B later, if there's an easier or harder way. And then also, let's see, there's a definition that, I don't know, we won't ask about it on the exam or anything, but just in case it's in the homework, we say that events A and B are mutually exclusive. You might have already heard that, you know, in everyday language. Oops. Let's see. If the two events cannot occur simultaneously. So I guess, what would be an example of that? I guess if you want, you can do the playing cards. It would be, like if I draw one card from a standard deck, and it is, let's say A is the event that it is a king, and B is the event that it is a, I don't know, 10. Well, those are mutually exclusive because you can't have a king and a 10. A card's either a king or it's a 10. It's not both. So that's just an example of something, or an example of mutually exclusive. Okay, so again, yeah, we're not really going to worry about it too much, but just in case you see it in the homework. Okay, so we got or probability down. How about and probability? So if you want to know the probability of one thing happening and the other thing happening at the same time, it's really just the two multiplied together. Probability of A times the probability of B. And it's kind of similar to, what was it that we saw in a couple sections back? Or we'll see it, we'll see it in the future. The counting principle. Oh no, we saw it, well, yeah, we saw it, huh? I'm sorry. With the tree diagrams. I forgot about that. Yeah, so it's kind of that reason. You multiply because you want this to happen and this to happen. So that's again where A and B are events. And event A is assumed to have occurred as we calculate probability of B. So that's the thing that the little formula doesn't tell you. So you calculate, I'm going to highlight what we calculate here. Probability of A, so whatever, you don't even worry about B yet. But once you calculate the probability of A, and you move on to try to calculate the probability of B, you have to calculate the probability of A as if, calculate the probability of B as if event A has already happened. So that's kind of a confusing thing. So let's see. An alternate version of this formula, which is actually more useful, I'd say, I mean, as long as you remember what it means, is the probability of A and B is not the probability of A times the probability of B, but the probability of A times the probability of, this is the probability of, B, given that A occurred. That's what that not terminology, that the way, I don't know, the way they write it, that's what it means. It's like the probability A vertical bar B. That means the probability of B given that A has occurred. And that would only be important if A actually affects B. And I know that's kind of hard to imagine right now, but we'll see. Actually, in the very first example, that'll help us, I think. Oh, no, sorry. A few examples from now. But let's just jump into it. Example 1. The people waiting in line for a sandwich at the deli have ticket numbers 12 through 21. Okay, I might write that down so I don't forget. If one of these people's orders is prepared at random, what is the probability that the number is an even number or a number less than 15? Okay, so let's say event A is the event that the ticket is an even number. And then B is the event that the ticket is ticket number, what's it say, greater than or less than 15? Number less than, okay. There's a number less than 15. Okay, well, since it's an OR probability, we're going to need that formula. Probability of A or B is the probability of each of them added together, and then, minus the probability of them both happening at the same time. So we'll have to calculate each of those separately. Let's see. Maybe off to the side I'll go. Alright, what is the probability of A? Well, remember, A is the event that we get. A is the event that the ticket number is even. So it's going to be, okay, the number of ways you can get an even number over the total number of outcomes. Okay, number of ways to get an even number. So basically, how many even numbers are there between 12 and 21? And the total number of outcomes. Let's see, okay, so I just got to figure out how many even numbers are there from 12 to 21. Okay, let's see, there are 12, let's see, 13 no, 14, 15 no, 16, 18, 20. So there are 5 ways you can get an even number between 12 and 21. And you're including 12. 12, 14, 16, 18, and 20. The total number of outcomes is just how many numbers are there from 12 to 21. 12, 13, 14, 15. You don't have to write this out, it's just, I don't know, you can count these on your fingers or in your head or whatever you want to do. Okay, how many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I think. So you have a 5 out of 10 shot, but that's a half, right? Huh, okay. Yeah, there we go. So 1 out of 2 shot of getting an even number. And then let's see, now we want to calculate probability of event B. Okay, so now what's the probability of event B happening? Probability of B. Just kind of a similar formula, right? The number of ways a ticket can be less than 15. Number of ways you get a number less than 15, and then we know the denominator is going to be the same. It's still the total. Probabilities are always out of the total. So 10 is the same denominator. But let's see, how many ways are there to get a number less than 15? Okay, well there are, what numbers are less than 15? We've got 12, 13, 14. That's it. And they said exclusively less than 15, not equal to. So I'm not going to include 15 on that one. There are only 3 numbers that fit the bill out of the 10. Alright, so we know the first 2 numbers in that formula. It was a half here and 3/10 here. Well, let's see, probability of A and B. Let's calculate that guy. Probability of A and B. All right. That's the number of ways you can have both. The number is, what do we say, even first we want. And also we want it to be less than 15. So let me just look at the numbers. We actually have them here. Let me see. Where's, oops. These are all the numbers that we already listed them. How many of those are even and less than 15? Well, the only ones are the 12 and the 14. So there are only 2. 12 and 14. 2. And it's still out of the total, so I'm not even going to write that. 2 out of 10 or 1/5. Alright. So far, so good. Okay, so I think we got... Okay, now that we're about to subtract some fractions, I realized that even though I had reduced these fractions if I want, I can go back to their unreduced forms. Because remember, 1/2 came from 5/10, and then 3/10 didn't reduce anyway, so no need to do anything with that. But the 1/5, I think that came from 2/10. Yeah, and that way they have the same denominator, and I'm actually able to calculate. Okay, I'm actually able to calculate the answer. So it's just adding and subtracting the numerators. 5 plus 3 is 8. Minus 2 is 6. We got 6/10, but that reduces to 3/5. Okay, so the answer there is 3/5. Alright, let's look at the next example here. 2 cards are dealt from a deck of cards. So remember the standard deck of cards, how that works. What do we have? They want us to first find the probability of being dealt 2 cards that are both kings if the cards are dealt without replacement. Okay, so that might be a language that you're not familiar with, but it's kind of what you would think it would be. The cards are dealt without replacement. That means once the first card is dealt, it is no longer an option for the second card, which is usually the case when you play cards, right? Usually you don't take one card, put it back. Yeah, you don't take one card, put it back, and then choose a separate card. Usually you take one, keep it, and then take a second one. But in part B, we'll see that you can also talk about with replacement, which means once the first card is taken, you put it back before you grab the second card. And that means it's an option for your second card. So you could conceivably in part B get the same card twice, but in part A you can't. Okay, so let's see. Okay, so next example, 2 cards are dealt from a deck of cards. So this is what we were talking about, yeah. Without replacement versus with replacement. So let's see. The probability of being dealt 2 cards that are both kings. Okay, so I guess that's like you're saying the probability that the first card... you know what? I'm going to start writing out the events. I mean, you definitely don't have to do this, and I think once you feel pretty comfortable, you won't have to do this, but let's see, so what are the events? Let's say event A is the event that the first card is a king, and event B is the event that the second card is a king. Okay, then we can rephrase this problem to ask, instead of what's the probability that both are kings, it's what's the probability that event A happens and event B happens. Okay, and then according to the formula, that's the probability that event A happens multiplied by the probability that B happens, but you got to assume that event A has already happened. And that's the way, like we said, that's the notation for it. So the probability of event A happening, I think we've seen this before. There are 4 kings in a deck of cards out of 52 total cards. So that's the probability of event A happening. But now we got to think about if event A has happened, okay, and we said without replacement. So once we calculate the probability of B, which is the second card is a king, there's 1 king missing from the deck. The deck, because it was the first card that we chose. Event A. Okay, so there's 1 less card to choose from. That means there are only 51 cards left in the deck. And there were 4 kings, but now there are 3 kings left. 3 kings left. 51 cards left in the deck. There we go. So, and I think this reduces. I think 4 and 52 reduce. Let's see. Like 4 goes into 52 13 times. And I believe 3 goes into 51, let's see, 17 times? Is that right? Yeah. So you're left with 1 over 13 times 17 is 221. Wow. So you don't really have a very good shot, right? 1 out of 221 shot of getting 2 kings, so not great. Don't expect that to happen, right? And then if you're familiar with cards, if you play Texas Hold'em, I think that's how the game starts out. You're dealt 2 cards. So if you're thinking, oh, that'd be nice if someday I got a king, or 2 kings, yeah, that's very rarely going to happen, so don't expect it. Oh, yeah? See? The baby agrees. So part B, find the probability of being dealt 2 cards that are both kings if the cards are dealt with replacement. So, okay, it's the same thing, but when we calculate the probability of B, given that A has already happened, yeah, probability of A happening is the same, because you only took 1 card out, you had a 4 out of 52 chance of it being a king. But if you put the card back in, there are still 4 kings left, and there are still 52 cards left. After putting the king back in, there are 4 kings and 52 cards. And those both can be reduced like we saw in the previous part. Oops. Yeah, both reduced to 1/13, right? Like we said, because 4 goes into 52 13 times, so it's 13 times 13, 169. You have a 1 out of 69, or sorry, 1 out of a 169 shot of if you replace the first card, you get a king on the second card. So not much of a better shot than if you didn't replace, huh? Alright, how about part C? Find the probability that the first card or the second card is a king, first with replacement and then without replacement. Okay, well either way, since it's a OR, we're going to use the OR formula. Probability of event A plus the probability of event B minus the probability of both happening. Okay, and the good thing is we've calculated the probability of event A and event B happening in parts A and B. So first, with replacement. Okay, then it's going to be probability of event A was, what would we say, 4 out of 52 plus... Okay, notice that this is probability of event B here. It doesn't say that you're assuming event A happened. So you don't need to consider event A. So just imagine the second card was a king. It doesn't matter what happened to the first card. So imagine the first card never happened. It's just this new card. There are 4 kings out of 52. Yeah, if this were meant to be, what's the probability of event B having, I guess having event A had happened, then they would have written it like this, like we saw in the other formula. So since it's not like that, it's just calculate the probability of event B, and you don't need to assume event A happened. Okay, and then the probability of event A and B happening, this is with replacement. That was from part, which one? Part A. I think, what did we say? It was 1 out of 221? Is that right? Okay, so that means we need to find a common denominator here. Alright, and this is a pretty complicated problem as far as fractions go, but the LCD here is 884 between 221 and 52. So let's see, we need to multiply 52 by 17 to get there. Let's see, so we'll multiply these guys by 17, top and bottom. Because 17 times 52, oops. Okay, and then 221 needs to be multiplied by 4 to get there. Okay, and then we have the numerators are 4 times 17, which is 68 out of 884. That's the first fraction. The other fraction is the exact same. The last one is 4 out of 884. Okay, so what happens if we add and subtract those? We get 136 minus 4, 132 out of 884. And I think that reduces by 4 at least. Let's see. You get 33 out of 221. That'll be the guy. Okay, so I don't know. Don't worry about the fractions. Won't be that big on an exam. That's just, I guess, for an example. And then let's see, without replacement, the only difference will be because the first fraction it doesn't matter if it's replacement or not. The probability of A and the probability of B. It's only this probability of A and B. We'll use the one we got from part B in this problem. It was 1 over 221. The probability of getting 2 kings. And then let's see. I think that's a little easier because the common denominator is... Oh, wait. Whoops. Oh, no, sorry. I'm looking at the wrong... It was 169, huh? Hello. The common denominator would be 676. So So it's going to be something over 676 plus something over 676 minus something over 676. See, 52 times 13 is 676. So we'll multiply that first fraction by 13, same with the second fraction. And 169 times 4 is what we need to get 676. So the first numerator becomes 52, as well as the second numerator because they're the same fraction. The last one is a 4. So let's add 52 and 52 is 104, minus 4 is just 100 over 676. And I think that reduces by... Does 4 go into that? Let's see. Well, of course, that's how we got 676, huh? So that reduces by 4 to leave us with 25 out of 169. Bless you. Okay. Part D, find the probability that the first card is I wrote all over it, a red card or a face card. And the second card doesn't matter. Okay, so just imagine we're just drawing one card now, I guess. So now my event A is, what is it? The first card is a red card. I'm just going to say the card is a red card because we're not even talking about the second card. And then event B was, what did they say, a face card? Yeah, face card. Is a face card. Okay, so I want to know, what's the probability of drawing one or the other? Okay, well that's the formula. Or B, we need probability of A plus probability of B minus probability of A and B. Alright, so the probability of A, let's see, a red card. Half the cards in a deck are red cards. And there are 52 total cards, so half of 52 is 26. Because there are, yeah, 26 red and 26 black cards. That's half-half. And then, let's see, B is face cards. Let's see, there are 4 kings, 4 queens, and 4 jacks. Those are the face cards, which means total of 12 face cards. So there are 12 out of 52 probability of getting a face card. And the probability of getting a face card and a red card, well, let's just count. A and B. Okay, there are 2 red kings, 2 red queens, and 2 red jacks. That's a total of 6 cards. So 6 out of the 52 are, excuse me, red and face cards. Okay, so let's see. Let's come, and thankfully, I could reduce these fractions if I wanted to, but I'm about to add and subtract. So if I reduce, they might have different denominators, which will kind of hurt me. I'd rather add and subtract first, and then reduce if if it's possible. So let's see. 26 and 12 is 38. 38 minus 6 is 32 out of 52, and that reduces by 4 to leave 8 out of 13. Is that right? Yeah, I think so. There we go. It's got an 8 out of 13 shot of a random card being drawn being either a red card or a face card. That's pretty good. That's better than 50-50 odds, right? Yeah, okay. The last part of this problem, find the probability that neither card is red. Okay, so that's a little weird. So that, I guess we're saying event A is that the first card is, let's see. You know what? Actually, okay, sorry. You know what? This one I think we can use. Remember from a previous section, the probability of an event not happening is 1 minus the probability of it happening. So, because I see the word neither, it kind of sounds like the opposite of something. You know, the opposite of it being red. So what is, if that's event A not happening, neither card is red, then event A would be 1 card is red, at least one of them. Or you don't, well, we could use that formula or we don't have to, I don't know. I feel like maybe it's overkill here. We could use it where event A is the first card is red, and B, second card is red. And we could calculate the probability of A or B. I don't know if we already did that, that might be easier. Have we done that? First card or the second card is, well, we did a king, huh? We didn't talk about a red card yet. Okay, so since we haven't calculated that, maybe it's just easier to do it straight up, huh? So we want neither card is red. That means, let's say event A is the first card is not red, and event B, second card is not red. Okay, then what we want is probability of A and B, because it's not it's not like it sounds like I'm okay with a red card, or I'm not okay with one of them being red. I'm okay, I don't want either of them to be red, so it must be that event A, the first card is not red and the second card is not red. Okay. And that one I can use the formula. What's the probability of A happening multiplied by the probability of B happening given that A has already occurred? So okay, not red. You know, if you want, you can say first card is not red. Another way to say that is the first card is black, right? Because there's only red and black cards. So if someone says, "Oh, I want my first card not to be red," that's the same thing as saying I want my first card to be black. Same thing with the second card. The second card is black. Yeah. So anyway, what's this guy doing here? First card is black. Well, half of the deck is black, so 26 out of 52 multiplied by, okay. Now we're talking about without, let's see, without replacement. So I guess if they don't tell you is with replacement or without replacement, you assume it's without replacement if it's not mentioned. If not mentioned. Yeah, especially with cards, you know, because if I say I'm dealing you 2 cards, usually I don't give you a card, take it back, and then give you another card, right? I let you keep the first card, and then I choose another card. Okay, so once this card, there's 26 black cards, and 52 total cards. Okay, if I take one of the black cards out, there are 25 left. 25 black, sorry, there's so much writing, cards left. And there are only 51 total cards left. 51 total left. After I took the first black card out. Alright. Let's see, does this reduce? Yeah, actually the first fraction reduces by... Actually 26 goes into both, so it reduces quite a bit. 26 goes into 26 once. It goes into 52 twice. And I think that's all we can reduce, so I'll multiply across. 1 times 25 and then 2 times 51. So you have a 25 out of 102 shot of neither card being red, or in other words, both cards black. So that's true. A lot of these probability problems, the way they're phrased is confusing. So if you just want to rephrase it, don't feel bad. All right, now let's try example 3. What do we have? A couple plans to have 3 children. Find the probability that first all 3 children are boys. Okay, so this is probably easier, especially if you're not familiar with playing cards. So all 3 children are boys. So I'm going to say, I'm going to have a little spot for each child and their probability. So here's child 1, here's child 2, and I'll calculate the probability of him being a boy. 2 times child 3. And we're going to multiply the probabilities because I guess what we're saying is we want event A, first child is a boy. Event B, second child is a boy. Then event C, third child's boy. What we want is a probability of A and B and C. So, and we know from above that you multiply the probabilities. And if we just keep in mind we can't replace, that'll help. Or, well, replacement doesn't make sense. So what is the chance that the first child's a boy? 1 out of 2, right? Because there's only 2 sexes. You have boy or girl. And then I only have 1 choice for what I want because I want a boy. And then same thing with the second child. There's 1 out of 2 shot of getting a boy. Yeah, because, you know, if the first child's a boy, that doesn't affect the probability the second child's a boy. Even though it kind of feels like it does. You know what I mean? It's like, oh, well, I had a boy, so chances are I'm going to have a girl next. But that's actually not true mathematically. So this is one of those times where we'd say that these events are mutually exclusive. So just the fact that the first child's a boy or not a boy doesn't matter. It's not going to affect the second child. So that's why you're not seeing different fractions here. It's just all 3 are the same fraction. And not like with cards. You know, if I'm dealt a card and I get a king, that's going to affect whether I get a king on the next card because I already have a king. There's 1 less king in the deck, and also there's 1 less card in the deck total. But with these, that's one thing we might want to note is that these events are mutually exclusive. I think we defined that above, right? What it means. Mutually exclusive. Yeah. Oh wait, sorry. Not mutually exclusive, or not. Sorry, I should say that. Mutually exclusive means that they can't happen at the same time. Of course these can happen at the same time. I'm losing my mind. It's that these aren't... what I should have said, these events are independent. That's what I should say. And I don't know if we said it before, but this might be useful, or you might even suspect it already, that if you have independent events where, you know, if one happens or doesn't happen, it doesn't affect the other guy's probability. With independent events, if you calculate the probability of one of them happening, given that the other happened, it's the same as if you calculate the probability regularly, because, well, obviously because the first thing happening or not happening doesn't affect the probability of the second thing happening. So anyway, that's the only time that those formulas are equal. The first one we wrote for the AND probability, and the second one. It's when you have independent events. But how about part B? The middle child is a boy and the other two are girls. Well, this one's actually tough, excuse me, tough to calculate. Because I think if we were to do the same thing we did last time, there's a half chance and a half chance and a half chance, then it wouldn't take into account that we want the middle child to be a boy. Yeah, because if you did it this way, whereas you have a 1 out of 2 shot of getting a girl for the first one, a 1 out of 2 shot of getting a boy for the second one, and then 1 out of 2 for a girl, then that means, I guess that's more specific. So what we could do, you know, is think of all the possibilities. I think, if you ever stuck with probability, just think of the sample space, or all the things that can happen. Let's see, I can have 3 boys, I could have 1 girl and then boys, I can have a boy with a girl in the middle, 2 boys and then a girl. So that's all the ways I can have 2 boys. How about 2 girls? It could be girl, girl, boy. It could be a boy in the middle, girl, boy, girl. It could be the boy in the beginning, boy, girl, boy. And I think the last one I'm missing, oh sorry, boy, girl, girl. I'm losing it. And the last one is 3 girls. Those are all the total. And that's why I noticed there are 8 options, 8 possibilities. And that's how we could have done part A, is there's 8 possibilities and we only want 1 of those, the 3 boys, 1 out of 8. So we could have done that in part A. In part B, the middle child's a boy and the other 2 are girls. Where's that? That would be this one, huh? There's only 1 out of the 8 again. And then how about at least 1 child's a girl? And then you can just count. How many have that? 7 out of the 8 have at least 1 child a girl. Yeah, so sometimes if you're stuck, the easiest way to do it is just list all the possibilities and then count how many of those possibilities have what I want, and then go from there. I guess that doesn't always work, because like with cards, it's kind of hard to count all the, I don't know, everything with cards. Alright, let's try this one. This one looks kind of fun. This is probably more up my alley, like picking movies. Let's see, Tim owns 15 movies at home. 5 are comedies, 7 are action movies. 5 are comedies, 7 are action movies, 2 are... Alright, we got 5 comedies, and what else? 7 action movies, 2 horror movies, 1 drama. Alright, I guess that might be worth writing down somewhere that I won't lose it. Let's see, 5 comedies, 7, would they say action? And then 2 horror and 1 drama. Okay, sounds good. 2 horror, 1 drama. I hope that adds up to 15, right? They said there were 15 movies. That would make sense. Okay, now, Tim's friend selects 2 of his movies at random. Find the following probabilities with replacement and without replacement. Okay, so for each of these parts, A, B, and C, we're going to do 2 little parts. 1 with replacement and 1 without. Replacement. So that would be like, I guess his friend grabs a movie, you know, sees what it is, oh, it's action, or oh, it's comedy, takes note of it, and then puts it back, and then grabs a random one. So it could have picked the same one twice, whereas without replacement, that means you took one out, you're not going to take the same one again, you're going to take a different one. So of course we're going to get 2 different probabilities there. But okay, a horror movie and then a comedy. Well, let's see, it's the probability of A and B, because you want the first one to be horror and the second one to be comedy. So I guess you're saying A is the first is horror, B would be the second comedy. And you want to make sure both of those are happening. So we're going to multiply the probabilities. Probability of A times probability of A given that B. So we'll start with maybe part A. It's without replacement. Or sorry, with replacement. So the probability of the first one being a horror movie is, well, how many horror movies are there? 2 out of the 15 total. Let's see, but since he's putting it back, put that horror movie back. That means he could conceivably grab the same movie the second time, so he still has 15 to choose from the second time, but you want the second one to be comedy, right? So how many comedies were there? There were 5. There we go. So that's our probability, and we can go ahead and start reducing instead of multiplying across. I mean, you could multiply across and then reduce, but you might as well reduce first. 5 goes into 15 3 times. Alright, then we're left with 2 on the top. 3 times 15 on the bottom is 45. So you have a 2 out of 45 shot. And then without replacement, that means... Well, we're still going to use the same formula. Let's see, it just be applied a little differently. A. Okay, the probability of A is still the same. The horror movie, there are 2 out of 15 horror movies. But now you're not replacing that horror movie, so there's one less movie to choose from. One less movie to choose from, but the numerator's not going to change. It's still 5, like it was in the last one, because you took a horror movie out. There's still the same number of comedies. Still 5 comedies. Yeah. So it's only a little difference. The denominator is a little different, and this one can actually reduce quite a bit. So we can reduce across here. The 5 can go into the 15 3 times, but also the 2 can go into the 14 7 times. Let's end up with 1 over 21 for that guy. Okay, let's try part B. So we'll do a similar thing. I'm not going to write out the formula. I think we get it now. Both are action movies, so what's the probability of the first one being action and the second one being action? So this would be probability first action, and it's with replacement. And this will be the probability that the second one is action. And if you replace that movie. So that means that both denominators are going to be 15, because first you're picking out of 15 movies, and then you're putting it back, so there are still 15 movies to choose from when you choose the second movie. And how many action movies were there? What'd they say? I forgot already. 7 action movies. So you have a 7 out of 15 shot of getting the action movie for the first movie, but also you're going to put it back, so you're going to still have the same probability of getting an action movie the second time. And those don't reduce, so I'm just going to multiply across. 7 times 7 is 49. 15 times 15... Okay, that's 225, I believe. 15 times 15. And that doesn't reduce, so we might as well leave it there. And then part 2, similar thing, except we're saying we are not replacing. So yeah, the first probability is always the same, because you haven't done anything yet. You're just finding the probability of the first one being a comedy, or sorry, an action movie. But now that there's one movie less, there are only 14 movies to choose from, and 1 less action as well. So there's 1 less movie to choose from total. And also 1 less action movie. So there's no longer 7 in the numerator for the second fraction. It's going to be 6. 1 less action movie. Okay, and let's see. I think we can reduce a little bit at least. Alright, we can do some reducing. See, the 7 can go into the 14 twice. And I know 6 and 15 reduced by 3. 3 can go into 6 twice. 3 can go into 15 5 times. And then also the 2's can cancel vertically there. So you're actually only left with 1 on the top and 5 on the bottom. 1 out of 5 probability. Okay, at least 1 comedy. You know what? This is a good time to point out at least 1 is always a tough probability to calculate. So what we do is we think of the opposite instead. Think of the opposite. Then we'll use that formula. What was it? It was like if you know 1 probability the probability of that not happening is 1 minus the probability of it happening. So that's what we'll do. So that's kind of why that formula is useful. So far, it's kind of been optional. We could have used it a few times, but I don't know, it wasn't really helpful. But now this is where it's really important. When you see at least one, anything, even in a different problem, what's the probability that at least one of these things is bleh? You're going to want to use that formula instead. So let's say A is, okay, what's the opposite of that? Opposite of at least one comedy. So let's say that's not true. I don't have at least one comedy. That would mean none are comedies. Or no, I guess I should say both aren't comedies. Or in other words, you want to calculate the probability of the first not being a comedy and the second not being a comedy. So that one we're going to do, that's an and probability. So we're going to do probability of A times the probability, of A given that B from that formula. And again, we're not really calculating the probability of at least one being a comedy yet. Right now we're just calculating the probability of the opposite of that, which is none are comedies. Because calculating the probability of none being bleh is always a lot easier than some being bleh. So let's see, okay, probability of A, that's the first not being a comedy. So it'd be, okay, there are 15 movies total. And then we want to know how many are not comedies. Comedies. Let's see, how many were comedies? There were 5 comedies. So the rest of them, 15 minus 5 is 10. The rest must be not comedies. Non-comedic movies. Alright, and the second one, and I'm assuming first part A we're doing with replacement? Yeah, with replacement. So okay, that one's not a comedy, but you put it back, so there's the same probability that the second one's not a comedy. Be the same thing, and those two reduce to 2/3, both of them. So I might as well reduce first and then multiply across. 4/9. Okay, but remember, that's not the probability we want. The probability that we want is going to be 1 minus that probability. Because we started with the opposite of that, not A. All I got to do is take 1 and subtract that guy. 4/9. And if you find a common denominator, that would be 5/9. Okay. Now let's try one more part where it's without replacement. So part 2, it's a similar thing. I'm going to say without replacement, the probability of not having neither being a comedy, in other words, at least one's a comedy, we're going to use the same formula. But let's first calculate this guy, the opposite of what we want, which is the probability that the first is not a comedy and the second is not a comedy. And then we're going to use that same formula, the probability of A times the probability of A given that, B given that A. It's okay. I think the first fraction is going to be the same because it's just the probability that the first one's not a comedy. Oh, sorry, 10 out of 15. There were 10 that were not comedies out of the 15 times. Okay, now we have not only one less movie to choose from, so that there are 14 movies left, but there's one less comedy. So instead of, one less non-comedy, sorry. Because we're assuming we took a movie that wasn't a comedy first. So there's one less of those guys, which makes it 9 left once you take 1 out. So let's see, this should be it. And it's really tempting to just stop after you calculate this, but remember, this is the opposite of what we want. Now vertically, this reduces to 2/3. This 3 can reduce with this 9 to leave a 3. And actually this 2 can reduce with the 14 to leave 7. So all you're left with there is 3/7. But the probability we want is the opposite of what we just calculated. So the probability of what we just calculated not happening is 1 minus the probability of what we just calculated. Okay, and that was 3/7. And if you find a common denominator, put the 1/1, multiply by 7/7, you're going to get 4/7.